I guess the reason why we did the paper is really just to check some of the foundations that are in the NASA model. Um, Really, one of the pillars for estimating energy in feed is the old uh, OARDC equation, which has been updated. But one of the things it assumes is how much energy is in fiber, and to get that energy, it relies on the assumption of the heat of combustion of fiber.
Hello, I'm Bill Weiss, and welcome to the Blackbelt Dairy Podcast. My guest today is Dr. Paul Kononoff, a professor and an extension specialist at the University of Nebraska. Welcome, Paul.
Thanks, Bill. Good to be here.
We're going to talk about a paper you did very recently, published in JDS Communications. It had to do with the energy value of NDF. Would you first just briefly say, tell us first who was the main author on this, and why did you do the paper? Why did you do the experiment?
So the graduate student that worked on this study was Jason Stupinski. He joined me from University of Delaware. He did an undergrad project with Lehman Kung, and then he came here to do his master's. He's currently now doing his PhD at University of Minnesota. I guess the reason why we did the paper is really just to check some of the foundations that are in the NASA model. Really, one of the pillars for estimating energy in feed is the old OARDC equation, which has been updated. But one of the things it assumes is how much energy is in fiber. And to get that energy, it relies on the assumption of the heat of combustion of fiber. And the assumption in that model is that fiber supplies 4.2 mcals per kilogram of energy, and that's based on the heat of combustion. So that was really the setup for this study. And Bill, as you know, the samples actually came from you. You sent them off probably just before you left the office there for retirement. And I had a graduate student here that worked on the samples.
I need to that original number wasn't based on any heat of combustion. It just said it's starch, and it's just the number from starch, because no one ever did what you did.
Yeah, so that's a good point. So the heat of combustion was general for carbohydrates, 4.2. Yeah.
So what all samples? What types of samples or NDF sources did you evaluate?
So first of all, I did set Jason out on a quick lit search. I said, Jason, just make sure nobody's ever done this before. He was unable to find anybody that's actually bombed NDF residues. And so the samples that he looked at included alfalfa hay, corn silage, cottonseed hulls, DDGs, grass hay, soybean hulls, and wheat straw. And then he also had feces and TMR, and those TMRs were fed a variety of diets. And I think what's important to note is that NDF was run using the ANCOM system, and it wasn't ash corrected NDF.
And did you use sulfite to reduce the nitrogen in it?
Yeah, sulfite was included in there.
And I assume amylase as well.
Yeah, that's right. Yeah.
Why did you pick the samples you picked? They're pretty diverse.
That was really, I think, how we landed on those samples. Is we just, we wanted samples that dairy nutritionists are putting the feeds that they're putting into the diet. And so obviously we're heavy on forages, but then including some of these high fiber byproducts. So basically to be, very transposable to what people are doing, looking at the fiber that they're feeding.
Did you expect or hypothesize that they'd be pretty similar in gross energy, or that they'd vary across those feeds?
As you know, NASEM assumes them to be identical. So if you start to think about what is in NDF residue. Obviously, you have cellulose and hemicellulose, but one of the other things that's naturally in that NDF residue is lignin. And even that, we don't know how much energy is in lignin. That people have tried to measure that. But generally, there's an expectation out there that the heat of combustion or the energy in lignin is actually higher. And so we did expect some variation depending upon the composition of that NDF and those feeds that were high in lignin. We did expect the heat of combustion to be higher.
And did you, like you said, you had cottonseed hulls, which would be pretty woody.
Yeah.
So was that did your hypothesis come out true then, based on lignin?
Yeah. So generally, I would say this was a bit of a surprise for us. On average, and just a reminder, we assume that heat of combustion to be 4.2, and on average, we actually observed all of those feeds to be 4.03. So it was actually lower. And cottonseed hulls had a heat of combustion. The NDF was 4. So it was actually a little on the lower side than we expected. And it didn't seem like it was sensitive to lignin.
Why do you think it's lower than 4.2? Because again, lignin is in there and it should have a higher heat than.
It's a great question. I think, I don't know if I have the answer. It's usually, but I think there's two things that could have affected our measures. As I mentioned, these were not ash corrected. So there could have been ash in these NDF samples. And so ash would contribute mass, but it wouldn't contribute a heat of combustion. So that's one reason. The other is that they still could have been contaminated with protein, and the heat of combustion for protein is also lower. So ash and protein contamination could be the two reasons why we saw that.
Was there enough variation in these feeds that each feed you need a different heat of combustion for different feeds, or are they close? You just use a better average or to get better energy numbers then?
So, I mean, I think if we're really fine tuning things, you may want to think about that. We did see that these feeds vary from 3.85 to 4.2. So I think maybe that's the question for the next committee. Is it really worth all of that work to capture this variation? I would maybe suggest for a number of reasons. We're probably good with 4.2, but indeed there is some variation. And when you deal with some weird situations, weird feeds at ridiculous proportions in the diet, you may want to rethink that. But I think for generally speaking, the 4.2 probably works pretty good.
Introducing Ultrasorb R3.0, Volac's comprehensive and complete solution to reduce the negative impact of naturally occurring toxins on ruminants. Ultrasorb R3.0 is a species-specific product designed to mitigate the effects of specific mycotoxins in the gastrointestinal tract of ruminants. Ultrasorb R3.0 also offers lipopolysaccharides binding capabilities. Endotoxins such as LPS can contribute to inflammation in ruminants, with energy partitioned to mount an immune response instead of production. Learn more about Ultrasorb R3.0 at volac.com.
But you wouldn't, if you had another chance to do this, the equation, you wouldn't change it to 4 just because that 4 fits your data better than the 4.2, which was a guess.
Yeah.
Leave it at a constant, but cut it to 4 rather than 4.2.
I mean, based on our, this early data, I don't know if I'm quite ready to adjust it to 4, but I think if given more samples and maybe a clearer understanding of the directionality of it, we may need to consider reducing that. I think it's a little early to make that suggestion, but 4 versus 4.2, that's probably enough of a difference to say, this is something we should account for.
Well, my last question here, are you going to continue? Are you going to do some more samples or hope someone else does?
No, I'm kind of excited about this. Bill, you and I got going on this just as you were heading out the door for retirement. And I think there's great opportunities. I think Our plan is to collect samples as we continue to do our energy studies and to drill down on it. It does take labor. The graduate student work hard. It takes some effort. But for the most part, I think we can continue to work on this area in a convenient manner. So yeah, I do plan to keep looking at this.
Great. I'm glad to hear that.
Yeah.
And thank you for your time. It's been an interesting discussion.
Thanks, Bill.